Hello Math 1314 students, let's begin lesson 5, Functions and their Graphs. This is probably the most important lesson of STEM algebra. We're going to start something new that is extremely important, functions. Up until now, up until lesson 4 and all the way to pre-algebra as a matter of fact, we have been studying mostly equations. Those algebraic manipulations and x expressions and y expressions, those kind of things associated to forming and solving equations, and then applications of equations, some modeling, and some visualizations of equations, some geometry, inequalities. That's a variation of equations in a broad sense. In short, we have been studying mostly equations. Same for intermediate algebra, elementary algebra, pre-algebra, all the same. Not anymore. Now we have a new focus, functions. And this is going to take the center stage until you complete calculus. Okay, let's begin. Functions. What is a function? Good question. I have to start, but we need some preparation. We cannot start right away. So as the first stepping stone toward functions, let's begin with Cartesian products. Let capital X and capital Y be non-empty sets. The Cartesian product capital X times capital Y is a set of all ordered pairs, small x comma small y, where small x and small y are coming from capital X and capital Y, respectively. Does it make sense? I don't know. If you understood all those symbolically, great, but maybe not. So let us solidify our understanding through a couple of examples. Let's say capital X is 1, 2, 3 and capital Y is AB. Then Cartesian products x times y is the set of all possible pairs. 1A, 1B, 2A, 2B, 3A, 3B, and that's it. First component has to be coming from x, so 1, 2, or 3. Second must be coming from y, so A of B. 3 elements in x, 2 elements in y. 3 times 2 is 6, and we covered all 6. There's no more. So that's an example of Cartesian product for finite sets. What about infinite sets? Here's an example. What if x and y are both the set of whole real numbers? In that case, we get r times r, which is r2, and the set of all ordered pairs, pair of real numbers. And what is this? Set of all ordered pairs, x coordinate, y coordinate. Oh, we are looking at points on coordinate plane. If you look at just x, which is r, or y, again r, we have a line. It's one-dimensional. So we have horizontal and vertical lines. Put together, we have a plane. What kind of plane do we call it? Cartesian plane? Cartesian coordinate? Yeah, same Cartesian product. Same person, same mathematician, Descartes. It's all because of Descartes that we are studying all these. So that's Cartesian product, and that's a contribution by Descartes. And we reviewed coordinate planes and Cartesian coordinates as well. All right, that's done, and I hope everybody is cool with this Cartesian product now. What's next? A relation. A non-empty subset of a Cartesian product is called a relation. Any non-empty subset will do. And if any point x comma y belongs to that relation, then we say x is related to y. So any subset will do. So if you have any collection of any ordered pairs, and that's a relation. So we have very few control here. It can be anything. But then again, this is a math course. We don't just want anything that's possible to consider. So let's focus our attention to some mathematical relations associated to some algebraic equations. Like this, for example. Yes, we have a subset of the Cartesian product, r times r, so x and y are both real numbers. But not everything. Only those x comma y that satisfies these equations. X squared plus y squared is equal to 1. You can visualize like this. It's a circle. Can you understand this is a circle? What is an equation of circle? Do you remember this? That's an equation of a circle, isn't it? Sorry about the typo here. A circle centered at h, k with radius r, but in this particular case, hk is 0, 0, and r is 1. So that we have this. And as you can see, we have a circle. Now let's look at this point, blue point. X comma y sits on the circle. Let's see, plug in x equals to 1 and y equals to 0. Is it true? Yes. 1 squared plus 0 squared is 1. That's true. In other words, 1 comma 0 satisfies this equation. In other words, 1 comma 0 belongs to this relation. As you can see from this visualization, it sits on the curve. So 1 is related to 0. Does it make sense? 1 is related to 0. What this red point says is 1 is not related to 1. If you plug in x is 1 and y is 1, we get this. Now is this true? 1 squared plus 1 squared is equal to 1? That's not true. So 1 is not related to 1, or 1 comma 1 does not satisfy this equation, or it does not belong to this R1. It sits outside the circle. Here's another example. This time let's consider a little bit different equation. X squared minus y squared is equal to 1, and that's going to give me a parabola like this. So that defines another relation. And let's see, looking at this blue point, 1 comma 0 sits on the curve. So it satisfies this equation. In other words, it belongs to this relation R2. Yeah, it belongs to this R2. So 1 is related to 0. Well, you can check. 1 squared minus 0 squared is 1. Yeah, that's true. So 1 is related to 0, as you can see from this blue point. Let's look at the red point. 0 comma 1 is not on the curve. So 0 is not related to 1. Let's see. Let's go back to this equation and check. X is 0, y is 1. What do you get? Is this true? No. Negative 1 equals to 1. That's certainly not true. And as you can see, red point is not on this curve. Here's another example. This time it's a parabola. By the way, this curve is called a hyperbola. This one is a parabola. Negative 1 comma 1. Negative 1 is related to 1, as you can see here. And 1 is not related to 2, as you can see from here, from blue and red points. And you can check if they satisfy this relation or not. So those are examples of relations. There are many more examples, but I think these 3 are sufficient in order to get some idea. We are still not ready to define functions. We need 1 more, 2 more actually, domain and range of relations. A relation has a domain and a range. Roughly speaking, the domain consists of all the x coordinates, all the elements of capital X, so all the x coordinates related to something in y. So here, all possible x values. The range is all the elements of capital Y, so all y coordinates that are related from something in x, so all possible y values. Here we have really elegant symbolic expressions, but a lot of students will find it really difficult to read. And if you read through these, it's a little bit easier to understand, but this is just a rough description, roughly speaking, basically. Still, a lot of students will find it difficult to understand. whether it's symbolic expression or whether because this expression is just rough explanation, not perfect explanation. Perfect explanation is here, but they're hard to read. So how do we reconcile this? 3 examples. Let's look at some examples here. I hope those will solidify your understanding, you see. Perfect explanations are difficult to understand. Rough explanations are easy to understand, but they are not perfect. Well, let's reconcile through examples, and here's a good example. We have this relation, x over 3 squared plus y over 2 squared equals to 1, which turns out to be an ellipse like this. And the domain is all possible x-coordinate values. Do you see the smallest is -3 and the largest is +3? Nothing here, nothing down there either. And between covered everything. All the x-coordinate between -3 and +3 are covered. You're looking at the domain, so look at all the horizontal movement. Ignore y-coordinate. Going up and down, just ignore those. Horizontally moving this way. And then nothing here, nothing there. How about the range? Same way. This is range, so look at only y-coordinate. Vertically, starting from -2, ending at +2. Nothing up here, nothing down there. In between, all covered. How about next example here? We have a hyperbola here, and this time the domain is a bit strange. To the left, it goes on forever. So -infinity. And please ignore it going up or down because we are looking at the domain, so only x-coordinate matters. So from -infinity to, got up to here, -3, and then we cannot move further, goes back down. And then we have a gap. And it restarts at +3 and infinity. So in the end, what do you get? We have 2 intervals, -infinity to -3 coming from the first curve, and then 3 to +infinity coming from the second curve. In between, we have a gap. So we have the domain like this. How about the range? Well, look at the y-coordinate. Goes down forever, and then hits 0 and goes up forever. Covers everything. So -infinity to +infinity. How about the third example here? Domain, oh, that's easy, -infinity to +infinity. Horizontally, to the left, to the right, goes on forever. Do not pay attention to going up or down because you are looking at the domain, only the x-coordinate matters. How about the range? This time only y-coordinate matters. Down here there's nothing. We start from 0 and it goes up, 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 up forever. Either way. Please ignore going left or right because we are looking at the range. Only the vertical, or the y-coordinate matters. So starting from 0 and to +infinity. One more thing, we have to have a bracket here, not parentheses, because y equal to 0 at this point, yeah, that's part of the graph. It's possible. 0, 0. If you plug in 0, 0, it'll work out. So this point is okay. 0 is allowed. So we have to start from 0. It's bracket. And toward infinity, of course, we have to have infinity. No real number is equal to infinity or negative infinity. So always infinity. And as for having parentheses for some other situation, well, that's going to be showing up later. But at this moment, you didn't see any examples of intervals with parentheses with some starting number and ending number. Again, -3 here. That's possible. This -3 here. Yeah, that's part of the graph. So we have to have brackets. Later on in examples 1.8, we'll see some various examples where we have to consider some open intervals as well, but we're going to consider those later. Those are tougher examples, of course. So we went through relations. Are we ready to discuss functions? Yes, we are ready, and we are going to start doing that from the next video. See you soon. We'll start from functions.